This element existed for less than 2 seconds before vanishing forever. Scientists spent decades fighting over who actually created it first. No one has ever held a visible piece of this substance. It doesn't exist in nature. Humans had to build it, atom by atom. 2 Cold War superpowers turned this discovery into a scientific battlefield. By the end, you'll know how you weigh something that lasts milliseconds. This is a story of Dubnium, element 105 on the periodic table, and it starts inside a machine that smashes atoms at near light speed. Dubnium sits in row 7 of the periodic table, among the superheavy elements. Its symbol is Db, its atomic number is 105. Nothing about it is simple. Every atom of Dubnium ever made was created by humans, not found. It belongs to a group called transactinides, elements too unstable to occur naturally. These elements only exist because physicists forced them into being. Dubnium's most stable form still only survives around 30 hours, at best. Most isotopes of it die in milliseconds, not hours. That instability isn't a flaw, it's the entire point of studying it. Every superheavy element teaches scientists how atomic nuclei hold themselves together. Dubnium is basically a stress test for the laws of physics. You cannot mine Dubnium. You cannot grow it. You must manufacture it. That manufacturing happens inside a particle accelerator, a machine built for collisions. Researchers take a lighter element and accelerate it to incredible speeds. Then they slam it directly into a target made of another element. The goal is nuclear fusion, forcing 2 nuclei to merge into one. Dubnium was first made by firing neon ions at americium atoms. Later experiments fused calcium ions with americium to confirm the results. This isn't a chemistry set reaction. It's controlled subatomic violence. The accelerator has to hit the target with millions of ions per second. Yet only a tiny handful of collisions actually create a new atom. Most collisions just bounce off or destroy the nuclei completely. Scientists call this searching for a needle inside a nuclear haystack. The odds of success are almost unbelievably small. Run after run, it can take weeks of continuous bombardment to produce one single atom. One successful fusion event might happen once every few hours, if lucky. And even then, the resulting atom starts dying immediately. Once created, a Dubnium atom is already racing toward its own destruction. Its nucleus is so overloaded with protons that it can't stay stable. Physicists call this the problem of nuclear charge repulsion. Too many protons crammed together means the nucleus wants to fly apart. So Dubnium undergoes radioactive decay almost the instant it forms. It typically breaks apart through alpha decay, ejecting a helium nucleus. That decay creates a completely different, lighter element in its place. This new element then decays again and again in a chain reaction. Scientists trace this entire decay chain to confirm what they actually made. It's like identifying a person only from footprints they left behind. No camera can ever directly photograph a Dubnium atom existing. Instead, detectors track the specific energy released during each decay step. Every element has a unique radioactive fingerprint in its decay pattern. Matching that fingerprint is the only proof the element was ever there. The technology of detecting a single atom, here's the wild part. Researchers work with exactly one atom at a time. There is no test tube, no visible sample, no beaker of Dubnium. Detectors called silicon strip arrays catch the decaying particles instantly. These sensors measure energy down to fractions of a million electron volts. Timing is everything. Since some isotopes vanish in under a millisecond, computers separate the real signal from thousands of false collision events. Researchers essentially fish one meaningful data point out of pure noise. This entire process can take months of accelerator time for one paper, and a single experiment might only confirm a few dozen atoms total. That's the scale scientists work at near the edge of the periodic table. Here's where the story stops being just physics and becomes politics. In 1968, Soviet scientists in Dubna claimed they created element 105 first. In 1970, American scientists in Berkeley claimed the exact same discovery. Both labs had genuinely different data, and both believed they were right. This wasn't a minor dispute, it became a defining Cold War rivalry. Each side proposed a different name for the same disputed element. The Soviets suggested Niels Bohrium, honoring physicist Niels Bohr. The Americans proposed Hassium after chemist Otto Hahn instead. For over 2 decades, scientific papers used to competing names. Textbooks in different countries literally taught different names for element 105. This chaos became known as the Transfermium Wars among nuclear chemists. It wasn't just about pride. Funding and national prestige were on the line. Whoever got credit for discovery got credit for scientific dominance. The dispute dragged on through the 1970s, 80s, and into the 90s. IUPAC, the International Chemistry Authority, finally stepped in to mediate. In 1997, they issued a final, binding decision on the naming. The element was officially named Dubnium, after the Russian town of Dubna. Berkeley's proposed name, Hassium, was retired from official use permanently. It was a diplomatic compromise, acknowledging Dubna's original 1968 claim, but credit for verification was still shared between both research teams. This is one of the few elements named to resolve a legal dispute. Why this research actually matters, you might ask. Why humans bother creating an element that dies instantly? The answer lies in something physicists call the island of stability. Theoretical models predict certain superheavy elements could last far longer. Some calculations suggest specific isotopes might survive for years, not milliseconds. Every element created, including Dubnium, tests whether that theory is correct. Each new isotope adds one more data point toward that island. Finding a truly stable superheavy element could reshape nuclear physics entirely. Dubnium itself helped refine the accelerator techniques used for later elements like flerovium and oganesson, or their discovery to this groundwork. In that sense, Dubnium was a stepping stone, not a dead end. Every failed or short-lived atom still teaches scientists something new. That's the uncomfortable truth about frontier science. Most results aren't permanent. Progress here is measured in single atoms, not kilograms or breakthroughs. And yet, without this patience, we wouldn't understand nuclear stability at all. So Dubnium will never be in your phone, your car, or your body. It will never have a practical use in everyday human life. Its entire value lies in the questions it forces scientists to answer. It proves that matter can exist even for less than a second. It proves that international rivalry can still produce shared scientific progress. Somewhere in a lab today, another team is chasing an even heavier element, and it all traces back to the atoms Dubnium taught us to catch.